Alright, welcome to another video. Today we'll be talking about the chain rule. So if you've watched the other videos on the product and the quotient rule, we're kind of just building a bunch of rules we can solve derivatives with. The chain rule is essentially a rule for composite functions. All that means is we have some sort of, let's just say, function, f prime of u, for instance, and we have this as like an outer function, so this is the outer one, and then this is the inner one, and we're just going to be multiplying it after the derivative of the outer one, we're multiplying it by the inner one. In other words, what this really is saying is if we have any kind of functions, we're going to be working our way from the very outer, and we're working our way in to get each function's derivative, and they're all going to be multiplied by each other. Once you know this fact, you can solve a lot more derivative problems. So let's try a few examples and see if you can't figure it out. So let's just say for the first one, we had f of x, and let's just say we had like a kind of a longer polynomial one. So 4 minus 3x. Let's just say it's to the fifth power. We want to choose an exponent that we won't be tempted to multiply it out, because when you have ones that aren't very high, you can FOIL it and just do it the way you've already learned with the power rule. But you'll soon figure out that actually doing it with the chain rule is a lot quicker, and it reduces maybe mistakes as well. So let's try the process. So what happens is, if you remember, the chain rule is just we're going to use the outer, and then we're going to work our way inside. So the outer function is this to the fifth power. So we're going to use the power rule on this one and just sort of use it in that way. So the power rule, we would bring the 5 down. So we're just going to do that. So we're bringing the 5 down, and then we'll just reduce the power by 1. So 5 minus 1 is 4. And then we're just going to take the derivative now of the inside. So we did the outer section, check. Now we're just going to work on the inner one. So the inner function would be this one right here. So 4, obviously a constant is 0. So negative 3x, we know the derivative of x is 1. And 1 times negative 3 is negative 3. So we know we're going to be multiplying it by negative 3. Now we just have to simplify our answer. So the way we do that is we just kind of, usually it's going to be simplifying any constants or lone x terms. So 5 multiplied by negative 3 is negative 15. So we just put negative 15 in the front here. So negative 15, 4 minus 3x to the fourth, and this is your answer. So if you were to FOIL this entire thing out, you would indeed get an answer that's equivalent to this one right here. So let's try a similar one as well. So let's say we had something like we can really use any function with this rule. So let's use trig then, because the same thing applies with trig problems. So if we had the sine of, let's just say, 7x plus 2, what would we do here? Well, we'd want to follow the same pattern of the rule. So first, let's take the derivative of the outer function, which is this sine part. It's the outer one. Okay, well, sine's derivative is cosine. And just like before, whenever we take the derivative of the outer, we want to rewrite everything just as it is on the inner one, because we're not taking the derivative of it yet. So that would be 7x plus 2, just how you see it. And then we're going to multiply that by the derivative of the inner. So 7x plus 2. So just like before, we just really need to focus on the 7x here. So that would be 1. So 7 times 1 is 7. So you would say that it's 7. And then really this is the answer, but we can just make it a little cleaner by putting the 7 out front, the constant. So 7 cosine of 7x plus 2. And that would be your answer right there. So like before, it doesn't really matter the function. All that really matters is that we're completing everything in the same exact way. Okay, so now let's try to incorporate other things as well, so other patterns to this, and see what we can do. So let's just say we had something a bit more difficult to work with. What if we had something like the root? So we're not dealing with something like not in terms of just a parenthesis anymore. What if it was a root of e to the x? Let's just say plus x, let's just say, okay? So what would we do here? Well, what we have to do is it's helpful to rewrite this, the root, in a form that maybe will make more sense. Okay, so what we want to do is we want to rewrite this as f of x equals to e to the x plus x to the 1/2 power, because as we know, that is the same thing. Okay, so now we can take the derivative using the chain rule. So we're just going to move the 1/2 out in front of this, so the 1/2 goes right here, and then we're just going to be subtracting the 1/2 by 1, or 2 over 2 is the same thing. So 1/2 minus 2 over 2 gives you a negative 1/2, which is perfectly fine. Don't fret about it being a negative. It works. And we just finished the root part. Now let's go inside to this e to the x part. So we're multiplying by the inside's derivative. So e to the x, we know that derivative is just e to the x. And then x's derivative is just going to be 1. So e to the x plus 1. And now we can just kind of write this a little bit cleaner. So if we wanted to write this in a little bit of a cleaner way, we want to first just kind of write what the first part would be in standard form is a little helpful. So we know this whole thing is a negative exponent, so it's raised to a negative exponent. So it's going to be 1 over this 2, because this is still 1/2, and then it's going to be e to the x, so we're just putting this down below, to the 1/2 power, and we're going to be multiplying it by the same thing, e to the x plus 1. Now we can do this a little better still, so let's go up here and continually try to simplify. So if we want to do that, first of all, let's go ahead and put this e to the x plus 1 on top, because that's the same thing as if it's multiplying just by the fraction. So if we add e to the x plus 1, we can put that right on top there. And then also what we can do is we know that to the 1/2 power is just the root, so we can say that that's going to be e to the x plus x. So the answer to this problem ends up just being e to the x plus 1 over 2 multiplied by the root of e to the x plus x. So even kind of more complicated problems, you can figure it out just the same if you just focus on following the rule each time. So let's do some more and see if we can do it in a similar way. So actually, let's do something involving something that maybe looks a little weird at first, but you can follow it just the same. So what if we had something like this? What if we had like 6 over, so just the constant, over x minus 3 squared? Could we do the same thing? We could, but it's a little bit more confusing when it's in this quotient way. Like I said, you could use the quotient rule here, but we want to practice using the chain rule, and we'll try to make it a product whenever we can, because it tends to be a little faster. So we can rewrite this as basically f of x equals 2, and remember, we're just rewriting it, so we're not using the rule yet, we're just rewriting it in a different way. So this can be 6 multiplied by x minus 3 to the negative 2 power. So we're just putting the positive exponent to a negative 1. And now we can take the derivative pretty easily. So let's first work on the outer function, so this negative 2 exponent. So let's bring the negative 2, it's going to be 6 multiplied by this negative 2, which is bringing it down, and then it's going to be x minus 3. And remember, with negative exponents, we minus 1, but that ends up increasing its power. So negative 2 minus 1 is negative 3. And we're going to be multiplying by still the same thing, the derivative of the inside. The only difference this time is that if you notice, the derivative of x is 1, and then this, of course, is just 0. So it ends up being just 1. So whenever you have a derivative of like a chain rule problem and there's an x, just an x by itself, and that's it, your inside function derivative won't really affect the actual result, because 1 times anything is just this original answer. So when we start simplifying it, the 1 kind of goes away. So 6 times negative 2 is negative 12, and this is x minus 3 to the negative 3 power. And technically this is the right answer, so you can ask your teacher if they are okay with negative exponents. If they're not, it's pretty easy to convert that out. So we put the negative 12 on top because it's still it's not a negative exponent value, and we just put the x minus 3 back on the bottom how it was kind of in the beginning. So the answer is pretty similar to how you just started. Negative 12 over x minus 3 cubed. And you would have gotten the same answer had you just done it with the quotient rule in that way as well. So what if we tried doing things that had more than one, almost more than one chain? So in all of our examples so far, we've had our outer function and then our inner function, and that's been it. But what if there was more than one inner function? What I mean by that, what if there were more layers? Like, what if it was derivative inception? Is it crazy hard to do? It's not actually. We can do it just the same. So if we had tangent squared of 4x, or we should make sure we specify it's f of x, how would we find the derivative? Well, we'd want to first, it's helpful to rewrite this in a different way. If you're not familiar with how this works, it's helpful to rewrite this. So we can rewrite this as the tangent of 4x, and then this whole thing is squared. So it's kind of just inferred that you understand that this is basically what it's telling you. But if you're not familiar or if you don't remember, don't worry, just rewrite it. It doesn't take that long, and that way you don't make a mistake. So, but if you notice, we're just going to do the same thing, but we're going to work our way from the outer to the inner. So the first part of this is the exponent part. So we're going to bring the 2 down, and then we're going to do the inner part will stay just the same. So tangent of the 4x, and then we're going to subtract 2 by 1. That's just to the first power, but we can put that here, but that's kind of invisible. Then we're going to multiply by the trig part. So we did the power. Now we're going to work our way inside to the trig. So tangent's derivative, we already know, is secant squared. So that's going to be secant squared of 4x. Remember, we're keeping the actual angle the same, so we're just keeping that the same. Now we're to the final function, the inside one. The angle is 4x. We know the derivative of 4x is 4, so that's just going to be multiplied by 4. And this is the entire answer. We just have to rewrite it and make it a little cleaner. Usually that, like I said, usually it's just constants you have to specify. So that's going to be 4 times 2. That's going to be 8. And then that's going to be 8, right? Tangent of 4x multiplied by the secant squared of 4x. So as you can see, not too bad of a process. It's the same thing when you have multiple things going on. You just have to take it one at a time, write the whole list of functions and the derivatives of each one, and then combine anything at the end, and then you do get the answer. Not too bad. I'm going to come back with a few more of these. I find that these are the most helpful to practice with the chain rule. Okay, so welcome to another example. It's very similar to the last one we did. We have kind of 3 chain rules we're going to have to incorporate here. So let's just start by rewriting this into a way we can kind of see a little better. So again, this is going to be the cosine, it's the same thing I should say, cosine of x squared to the 5th power. And we can rewrite it into this normal way at the very end. So once we have it this way, let's just take the derivative and see what happens. So, just like before, we start with the power. We bring the 5 down, so 5, and it's multiplying by everything in the inside just stays the same. So the cosine of the x squared is the same, and we just decrease it, the 4th power. Then we're going to multiply it. By now we're going to do the angle, so the trig here. So cosine's derivative we know is negative sine, so negative sine of x squared. And then we're going to multiply that by the actual angle. So x squared's derivative we know is 2x. We're going to move the 2 down, decrease the power by 1, so it's 2x. And this is our answer. We just kind of have to simplify and make it a little prettier. So we have 5, 2x, that's 10x, but also remember we have a negative here, which means that it's going to be a negative 10x. So negative 10x. Now we're going to do this part. So this is technically all right, but we want to usually rewrite it in the standard trig way. So we put the power back kind of in the middle, just like how it was at the beginning. So that would just be the cosine of, so it's the 4, removing the 4, just removing it in standard form, x squared, so cosine the 4th power of x squared, and then just like the same way, we have the sine of x squared, and because we already dealt with the negative, we can just put that as the sine of x squared. And if it helps too, totally good, you can put parentheses on the angles, just so that you can see where the new term starts and ends. So this is negative 10 x cosine to the 4th of x squared multiplied by the sine of x squared. And that is your answer. So let's try another similar example so you can get the hang of this. Because what I always say is if you can get pretty good at doing the chain rule with these 3 in a row, you've pretty much mastered for the most part. So what if we had something like the f of x is equal to, let's just say, the sine, maybe squared, of 3x. What would we do here? Well, the same thing can be applied. So we're first going to take the actual angle. So remember, I'm not going to do it in the same way as before, but this whole thing is squared, so we're going to move the 2 out front. Then we're just going to put everything else the same. And usually, you would want to make sure you have the power, but because it's a 1, the whole thing is to the first power. We don't actually have to do it this time. Then we're going to multiply by the derivative of the trig. So sine's derivative we know is cosine. So cosine of 3x. And finally, of the actual angle. So 3x's is just 3 from our previous problems. We know that. So we just have to simplify. So that would just be, again, we have this 2, we have this 3, so then it's 6 sine of 3x. And again, I'm putting the parentheses. You can do that of angles. It makes it easier to understand sometimes, times the cosine of 3x. And I just want to reiterate here that that there was a to the first power, so this whole thing here had a first power. But because it's the first power, we don't have to really carry it over and put the first power right here in the middle. But just like if it was like squared or something, we would put it just like this right in the middle of the angle when we were finished. But this right here is the answer. 6 sine of 3x, cosine of 3x. So this is kind of what you can expect from all of your problems involving the chain rule. Just know that later on I will do videos involving the exponentials and logs. The reason why I didn't incorporate any logs or exponents, if exponentials, in this chain rule video is because we haven't been taught the rules for derivatives of exponents in e's and ln's in logs. Once we have those two rules, because they're a little different, they require their own rule, we can use a chain rule on them. And in fact, when I upload the exponential and log derivative videos, you will see exactly how that process goes too. But this is it. This is how all of the everything else works for every other problem, and the chain rule just requires a lot of making sure everything is written correctly. So I hope this helped with the chain rule. Thanks for watching. I really appreciate it.